Hello everyone, thank you for being here today. I'm truly excited to share this moment with you. Let's sit back, relax, and enjoy the journey together. Tyrannosaurus Rex, meaning Tyrant Lizard King, stands as one of the most fearsome predators ever to walk the earth. First discovered in 1902, this massive theropod dinosaur has become an icon of prehistoric power and continues to fascinate scientists and the public alike through ongoing paleontological research. T-Rex lived during the late Cretaceous period, approximately 68 to 66 million years ago, making it among the last dinosaurs before the mass extinction event. These giants roamed western North America, from Saskatchewan to Texas, during a time when the climate was much warmer and more humid than today. The landscape consisted of subtropical forests, river deltas, and coastal plains divided by the western interior seaway. Adult T-Rex specimens reached impressive sizes of 12 to 13 meters in length and 4 meters in height, weighing an estimated 8 to 10 tons. The most distinctive feature was the massive 1.5-meter skull, housing up to 60 razor-sharp, serrated teeth that could reach 20 centimeters in length. These bone-crushing teeth were perfectly designed for tearing flesh and crushing bones. Recent studies reveal that T-Rex possessed exceptional sensory capabilities, including binocular vision superior to modern hawks and an acute sense of smell for detecting prey across vast distances. Interestingly, the small forelimbs, though only 1 meter long, were incredibly strong and capable of lifting 180 kilograms each. As an apex predator, T-Rex was primarily carnivorous, feeding on large herbivorous dinosaurs such as Triceratops and Edmontosaurus. With a bite force estimated between 35,000 to 57,000 newtons, T-Rex could easily crush bones to access nutrient-rich marrow. Scientific evidence suggests it was an opportunistic predator, both actively hunting and scavenging when opportunities arose. Fossilized feces containing bone fragments confirm that T-Rex consumed entire carcasses, including bones, demonstrating its role as a dominant force in late Cretaceous ecosystems. While traditionally viewed as solitary hunters, recent discoveries suggest T-Rex may have exhibited more complex social behaviors. Some evidence indicates possible pack hunting or at least tolerance of other individuals during feeding. Growth studies show rapid development during adolescence, with juveniles potentially occupying different ecological niches than adults, reducing competition within the species. T-Rex reached sexual maturity around 15 to 20 years of age, with maximum size achieved by 25 to 30 years. Like other dinosaurs, they laid eggs and likely provided parental care. The extended juvenile period suggests complex behaviors may have been learned rather than purely instinctual, indicating higher intelligence compared to other dinosaur species. T-Rex became extinct at the end of the Cretaceous period due to the catastrophic Chicxulub asteroid impact and subsequent environmental changes. However, their legacy lives on through birds, which are direct descendants of theropod dinosaurs. Tyrannosaurus Rex represents the pinnacle of terrestrial predator evolution, combining massive size, powerful weaponry, and sophisticated sensory capabilities. As paleontological techniques advance, our understanding of this magnificent predator continues to evolve, providing valuable insights into prehistoric ecosystems and the remarkable diversity of life that once dominated our planet. Rex remains an enduring symbol of the incredible adaptations that allowed dinosaurs to thrive for over 160 million years. Triceratops, meaning three-horned face, ranks among the most recognizable and iconic dinosaurs to have ever existed. This massive herbivorous ceratopsian dinosaur, first discovered in 1887 by paleontologist Othniel Charles Marsh, has captured public imagination with its distinctive skull featuring three prominent horns and a large bony frill. As one of the last dinosaur species before the mass extinction event, Triceratops represents the evolutionary pinnacle of horned dinosaurs. Triceratops lived during the very end of the late Cretaceous period, specifically the Maastrichtian stage, approximately 68 to 66 million years ago. This places them as contemporaries of Tyrannosaurus Rex and among the final dinosaur species before the catastrophic extinction event. Fossil evidence indicates that Triceratops inhabited the western regions of North America, with specimens discovered across Montana, Wyoming, Colorado, North Dakota, and Saskatchewan. During this period, the climate was significantly warmer and more humid than today, with no polar ice caps and elevated sea levels. Triceratops roamed the coastal plains and river valleys of Laramidia, an ancient continent characterized by lush subtropical forests, expansive floodplains, and diverse plant communities that provided abundant food sources for these massive herbivores. Triceratops was truly a giant among dinosaurs, with adult specimens reaching lengths of 8 to 9 meters and heights of 3 meters at the shoulder. Weight estimates range from 6 to 12 tons, making them comparable in size to modern elephants but significantly more robust. The most distinctive feature was the enormous skull, which could measure up to 2.5 meters in length and account for nearly one-third of the animal's total body length. The skull featured three prominent horns, two large supraorbital horns above the eyes that could reach over 1 meter in length, and a smaller nasal horn above the nose. Behind the skull extended a massive bony frill that could span up to 2 meters wide. This frill was decorated with small spikes called epiccipitals around its perimeter, creating an impressive defensive and display structure. The body was supported by 4 sturdy legs, with the front legs being shorter than the rear, giving Triceratops a slightly forward-leaning posture. The powerful limbs were necessary to support the enormous weight, particularly the massive head. Recent studies suggest that Triceratops could move at speeds of up to 25 km per hour when necessary, despite their bulk. As a herbivore, Triceratops possessed specialized dental adaptations for processing tough plant material. The mouth contained hundreds of small, sharp teeth arranged in batteries, continuously replaced throughout the animal's lifetime. These dental batteries were perfectly designed for shearing and grinding fibrous vegetation. The diet consisted primarily of low-growing plants including ferns, cycads, and flowering plants that were becoming increasingly common during the late Cretaceous. The powerful beak-like front of the mouth was used to crop vegetation, while the complex tooth batteries processed the plant material. Fossil evidence suggests that Triceratops could consume up to 200 kilograms of plant matter daily to sustain their massive bodies. Recent paleontological discoveries have provided fascinating insights into Triceratops' behavior. Evidence suggests these dinosaurs may have lived in small family groups or herds, particularly during certain seasons or life stages. Bone beds containing multiple individuals of different ages indicate possible social grouping, though the extent of herd behavior remains debated among scientists. The elaborate horns and frill likely served multiple purposes beyond defense. These structures probably played important roles in species recognition, dominance displays, and courtship rituals. Evidence of healed wounds on skulls suggests that Triceratops engaged in intraspecific combat, with individuals locking horns in competitive displays similar to modern rhinoceros or bighorn sheep. Like all dinosaurs, Triceratops reproduced by laying eggs. Growth studies based on bone histology reveal that these dinosaurs experienced rapid growth during their juvenile years, with significant changes in skull proportions and horn development as they matured. Young Triceratops had relatively small horns and frills that grew dramatically with age, suggesting these features were important for adult social interactions. The extended developmental period indicates that Triceratops likely provided some degree of parental care, with adults potentially protecting and guiding juveniles within family groups or small herds. Triceratops lived alongside formidable predators, most notably Tyrannosaurus Rex. The defensive capabilities of Triceratops were impressive, with the combination of horns, frill, and sheer size providing effective protection against even the largest predators. Fossil evidence, including bite marks from tyrannosaurs on Triceratops bones, confirms these dramatic predator-prey interactions occurred in ancient ecosystems. The forward-facing horns were likely used in active defense, while the frill protected the neck and vital areas. The robust build and low center of gravity made Triceratops a formidable opponent for any predator brave enough to attempt an attack. Triceratops became extinct at the end of the Cretaceous period, approximately 66 million years ago, as part of the mass extinction event that ended the age of dinosaurs. As one of the most abundant large herbivores of its time, Triceratops played a crucial role in late Cretaceous ecosystems. Today, Triceratops remains one of the most studied ceratopsian dinosaurs, providing valuable insights into dinosaur evolution, behavior, and extinction. The abundance of fossil specimens has made it a cornerstone species for understanding late Cretaceous ecosystems and the final chapter of the dinosaur era. Triceratops stands as a testament to the incredible diversity and evolutionary success of dinosaurs. With its impressive defensive features, massive size, and complex social behaviors, this three-horned giant dominated the herbivorous niche in one of Earth's most fascinating prehistoric ecosystems. The continued study of Triceratops enhances our understanding of dinosaur biology and the ancient world they inhabited, ensuring this magnificent creature remains an enduring symbol of prehistoric life. Velociraptor, meaning swift thief, is one of the most famous and misunderstood dinosaurs in popular culture. First discovered in 1924 by paleontologist Roy Chapman Andrews in Mongolia's Gobi Desert, this small but deadly predator has captured public imagination despite significant misconceptions about its actual size and appearance. As a member of the Dromaeosauridae family, Velociraptor represents a crucial link in understanding the evolution from dinosaurs to modern birds. Velociraptor lived during the late Cretaceous period, approximately 75 to 71 million years ago, specifically during the Campanian stage. Unlike many other famous dinosaurs that inhabited North America, Velociraptor fossils have been exclusively found in Central Asia, particularly in Mongolia and northern China. This geographical distribution places them in the ancient continent of Asia during a time when global sea levels were high and continents were positioned differently than today. The late Cretaceous environment of Central Asia was characterized by arid to semi-arid conditions, with seasonal monsoons creating alternating wet and dry periods. Velociraptor inhabited ancient river deltas, floodplains, and desert margins dotted with oases. The landscape featured sand dunes, seasonal lakes, and sparse vegetation, quite different from the lush subtropical forests that characterized other regions during this period. Contrary to popular media portrayals, actual Velociraptor specimens were relatively small dinosaurs. Adults measured approximately 2 meters in length, stood about 0.5 meters tall at the hip, and weighed between 15 to 20 kilograms, roughly the size of a large dog or small wolf. The body was built for speed and agility, with long, powerful legs designed for rapid movement and sharp turns. The most distinctive feature was the large, curved, retractable claw on the second toe of each foot, measuring up to 6.5 centimeters in length. This killing claw could be held elevated while running and deployed during attacks. Recent biomechanical studies suggest this claw was primarily used for climbing and grasping prey rather than disemboweling, as commonly depicted. Perhaps most remarkably, recent fossil discoveries have confirmed that Velociraptor possessed feathers. While these feathers were not suitable for powered flight, they likely served purposes including temperature regulation, display behaviors, and potentially gliding. The presence of feathers, along with other bird-like characteristics such as wishbones and wrist joints, strongly supports the evolutionary connection between dinosaurs and birds. Velociraptor was a carnivorous predator that likely hunted a variety of prey including small mammals, lizards, and other dinosaurs. The sharp, serrated teeth were perfectly adapted for slicing flesh, while the powerful jaws provided sufficient bite force for their size. Fossil evidence suggests they may have preferred prey smaller than themselves, though they were capable of attacking larger animals when hunting in groups. The famous fighting dinosaurs fossil discovered in 1971 shows a velociraptor locked in mortal combat with a Protoceratops, providing direct evidence of predator-prey interactions. This remarkable specimen shows the velociraptor with its killing claw embedded in the Protoceratops's throat area, while the herbivore's beak grips the predator's arm, suggesting these encounters were dangerous for both parties. Recent analysis of velociraptor brain cases indicates enhanced areas associated with balance, coordination, and spatial awareness, supporting theories of complex hunting behaviors and pack coordination. The large brain relative to body size suggests intelligence comparable to modern birds of prey. Evidence suggests that Velociraptor may have exhibited pack hunting behaviors, though this remains a subject of scientific debate. The discovery of multiple individuals in close proximity, along with trackway evidence from related species, supports the possibility of coordinated group hunting strategies. Such behavior would have allowed these relatively small predators to tackle much larger prey through cooperation and strategic attacks. The feathered display structures may have played important roles in social communication, species recognition, and mate selection. Like modern birds, different individuals may have exhibited varying feather patterns and colors for identification and social signaling within groups. Velociraptor reproduced by laying eggs, similar to modern birds and other dinosaurs. Nest sites discovered in Mongolia suggest that adults may have provided some degree of parental care, potentially incubating eggs and protecting young. The rapid growth rates indicated by bone histology studies suggest that juvenile velociraptors reached adult size relatively quickly, an adaptation that would have been advantageous in harsh desert environments. The extended learning period implied by their large brain size suggests that hunting techniques and social behaviors may have been taught rather than purely instinctual, indicating complex behavioral patterns within family groups. Velociraptor holds tremendous importance in understanding dinosaur evolution and the origin of birds. The numerous bird-like characteristics, including feathers, wishbones, and specialized wrist joints, provide compelling evidence for the dinosaur-bird evolutionary connection. Studies of velociraptor anatomy have revolutionized our understanding of how flight evolved and how modern birds inherited their remarkable abilities from their dinosaur ancestors. The discovery of feathers in Velociraptor and related species has fundamentally changed our perception of dinosaur appearance and behavior, moving away from the traditional reptilian imagery toward a more bird-like understanding of these ancient predators. Velociraptor became extinct approximately 71 million years ago, well before the mass extinction event that ended the dinosaur era. Climate changes and shifting ecosystems in Central Asia likely contributed to their disappearance, along with competition from other predators and changes in prey availability. Despite their extinction, velociraptors live on through their closest living relatives, modern birds. The evolutionary legacy of these swift hunters can be seen in the intelligence, agility, and predatory skills of contemporary raptorial birds. Velociraptor represents a fascinating example of evolutionary adaptation and predatory specialization. Though smaller than popular culture suggests, these feathered hunters were formidable predators perfectly adapted to their harsh Central Asian environment. Their combination of speed, intelligence, and deadly weaponry made them successful predators for millions of years. The continued study of Velociraptor provides invaluable insights into dinosaur behavior, evolution, and the remarkable transformation that led to modern birds, ensuring their place as one of paleontology's most significant discoveries. Stegosaurus, meaning roof lizard, stands as one of the most recognizable and iconic dinosaurs ever discovered. First unearthed in 1877 by paleontologist Othniel Charles Marsh during the famous Bone Wars period, this distinctive herbivorous dinosaur has fascinated scientists and the public with its unique combination of massive body plates and formidable tail spikes. As the most famous member of the stegosaur family, Stegosaurus represents one of the most successful herbivorous adaptations of the Mesozoic era. Stegosaurus lived during the late Jurassic period, approximately 155 to 150 million years ago, during the Kimmeridgian and Tithonian stages. This places them in a completely different era than famous dinosaurs like T. Rex and Triceratops, living roughly 85 million years before those late Cretaceous giants. Stegosaurus fossils have been discovered primarily in the western United States, with most specimens found in Colorado, Utah, and Wyoming, particularly in the famous Morrison Formation. During the late Jurassic, the climate was much warmer and more humid than today, with no polar ice caps and significantly higher sea levels. The landscape of western North America consisted of vast floodplains, river systems, and seasonal lakes surrounded by coniferous forests, fern prairies, and cycad groves. This environment provided abundant plant life that supported diverse dinosaur communities, including massive sauropods, various theropods, and armored herbivores like Stegosaurus. Stegosaurus was an impressive creature, measuring up to 9 meters in length and 4 meters in height, with adults weighing between 2 to 5 tons. The most distinctive features were the 2 parallel rows of large, triangular plates running along the back from neck to mid-tail, and the fearsome cluster of 4 long spikes, called the thagomizer, at the end of the tail. The iconic back plates, which could reach up to 60 centimeters in height, have been the subject of extensive scientific debate. Recent studies suggest these plates served multiple functions: thermoregulation through blood vessel networks, species recognition, and potentially defensive display. The plates were likely covered with a horn-like sheath and may have been brightly colored for visual communication. The body structure was uniquely adapted for low browsing, with front legs significantly shorter than the rear legs, creating a distinctive arched posture. The small head, measuring only 40 centimeters long, housed a brain roughly the size of a walnut, leading to the outdated myth of a second brain in the hip region, which was actually an enlarged nerve cluster for controlling the massive tail and hind limbs. As a herbivore, Stegosaurus possessed specialized adaptations for processing plant material. The narrow, pointed beak was perfect for selective feeding, allowing them to strip leaves and soft shoots from plants. The teeth were small, leaf-shaped, and designed for cropping rather than grinding, suggesting they relied on gastroliths, stomach stones, or extensive gut fermentation to break down tough plant fibers. The diet likely consisted of ferns, mosses, cycads, conifers, and other primitive plants available during the Jurassic period. The low-slung head position and flexible neck allowed Stegosaurus to browse on vegetation up to 1 meter high, occupying a different feeding niche than the towering sauropods that shared their environment. Studies of fossilized stomach contents and coprolites suggest that Stegosaurus could consume up to 200 kilograms of plant matter daily, requiring constant foraging to maintain their massive body weight. Stegosaurus possessed one of the most effective defensive systems in the dinosaur world. When threatened, they could swing their powerful, spiked tail in wide arcs, creating a deadly weapon capable of inflicting serious damage on predators. Fossil evidence, including a predator vertebra with a Stegosaurus spike embedded in it, confirms the effectiveness of this defense strategy. The back plates also served defensive purposes, making Stegosaurus appear larger and more intimidating to potential predators like Allosaurus and Ceratosaurus. Recent biomechanical studies suggest the plates could flush with blood to create dramatic color displays, similar to modern iguanas, serving as both warning signals and intraspecific communication. Evidence suggests Stegosaurus may have lived in small herds or family groups, particularly during migration or breeding seasons. Trackway fossils indicate coordinated movement patterns, though they were likely less social than other herbivorous dinosaurs. Like all dinosaurs, Stegosaurus reproduced by laying eggs. Recent discoveries of juvenile specimens reveal that young Stegosaurus had proportionally smaller plates and spikes that grew dramatically as they matured. This suggests the defensive and display functions of these features became more important with age and sexual maturity. Growth studies indicate that Stegosaurus experienced rapid growth during their early years, reaching adult size within 10 to 15 years. The extended development period suggests some degree of parental care, with adults potentially protecting juveniles within family groups. Stegosaurus represents the pinnacle of stegosaur evolution, showcasing remarkable adaptations for herbivorous lifestyle and predator defense. The success of their body plan is evidenced by the widespread distribution of stegosaurs across multiple continents during the Jurassic and early Cretaceous periods. The unique combination of passive defense, armor plates, and active defense, tail spikes, demonstrates evolutionary innovation in response to predation pressure from large theropod dinosaurs that shared their environment. Stegosaurus coexisted with formidable predators including Allosaurus, Ceratosaurus, and Torvosaurus. Fossil evidence of bite marks and damaged bones reveals the intense predator-prey dynamics of late Jurassic ecosystems. The defensive capabilities of Stegosaurus were clearly effective, as evidenced by their evolutionary success and abundance in the fossil record. Stegosaurus became extinct near the end of the Jurassic period, approximately 150 million years ago, likely due to climate changes and the evolution of new plant communities that affected their food sources. However, other stegosaurs continued to thrive into the Cretaceous period in Asia and Europe. The legacy of Stegosaurus extends far beyond their prehistoric existence. As one of the first dinosaurs to capture public imagination, they have become cultural icons and continue to contribute to our understanding of dinosaur evolution, behavior, and extinction patterns. Stegosaurus remains one of paleontology's most significant discoveries, representing a unique evolutionary solution to the challenges of herbivorous life in a world dominated by giant predators. Their distinctive appearance, effective defensive strategies, and successful adaptation to Jurassic environments make them enduring symbols of dinosaur diversity and evolutionary innovation. The continued study of Stegosaurus provides valuable insights into ancient ecosystems and the remarkable variety of forms that life has taken throughout Earth's history, ensuring their place as one of the most beloved and scientifically important dinosaurs ever discovered. Brachiosaurus, meaning arm lizard, stands as one of the most magnificent and awe-inspiring dinosaurs ever discovered. First identified in 1903 by American paleontologist Elmer Riggs in Colorado, this colossal sauropod has become synonymous with the concept of dinosaur gigantism. Distinguished by its unique body proportions with exceptionally long front legs, Brachiosaurus represents the ultimate adaptation for high-browsing herbivorous lifestyle during the Age of Giants. Brachiosaurus lived during the late Jurassic period, approximately 156 to 145 million years ago, during the Kimmeridgian to Tithonian stages. This places them in the same temporal window as other famous dinosaurs including Stegosaurus, Allosaurus, and Diplodocus. Fossil remains have been discovered primarily in the western United States, particularly in Colorado, Utah, and Wyoming, within the celebrated Morrison Formation. The late Jurassic climate was significantly warmer and more humid than today, characterized by high atmospheric carbon dioxide levels and no polar ice caps. The landscape consisted of vast river systems, seasonal floodplains, and extensive forests dominated by conifers, ferns, cycads, and ginkgo trees. This lush environment supported diverse ecosystems capable of sustaining enormous herbivorous dinosaurs like Brachiosaurus alongside other sauropod giants. Brachiosaurus was truly enormous, with adult specimens reaching lengths of 20 to 23 meters and heights of up to 13 meters, equivalent to a 4-story building. Weight estimates range from 35 to 80 tons, making them among the heaviest land animals ever known. The most distinctive feature was the unusual body proportions, with front legs significantly longer than rear legs, creating an upward-sloping back profile unique among sauropods. The neck alone could extend 8 to 9 meters in length, supported by massive cervical vertebrae with extensive air-filled cavities that reduced weight while maintaining structural strength. The small head, measuring only about 60 centimeters long, housed nostrils positioned high on the skull, an adaptation that may have helped with breathing at extreme heights or while feeding in water. The limbs were pillar-like and incredibly robust, necessary to support the massive body weight. Recent studies of footprint fossils suggest that Brachiosaurus could move at walking speeds of up to 12 kilometers per hour, despite their enormous size. The long tail served as a counterbalance to the extended neck and may have been used for communication through ground vibrations. Brachiosaurus was a specialized high-browser, uniquely adapted to feed on vegetation inaccessible to other herbivorous dinosaurs. The exceptional height allowed them to reach treetops up to 13 meters high, effectively creating their own feeding niche without competition from ground-level browsers like Stegosaurus or lower-browsing sauropods. The diet consisted primarily of conifers, including pine, fir, and redwood-like trees, along with tree ferns, cycads, and other tall-growing plants. The peg-like teeth were designed for stripping foliage rather than chewing, with food processing occurring through gastroliths, stomach stones, and extensive gut fermentation in their enormous digestive systems. Daily food requirements were staggering. Estimates suggest adult Brachiosaurus needed to consume 200 to 400 kilograms of vegetation daily to maintain their massive body weight. The long neck allowed efficient feeding across wide areas without moving the heavy body, conserving energy while maximizing food intake. Evidence suggests that Brachiosaurus may have lived in loose herds or family groups, particularly during migration or breeding seasons. Trackway fossils indicate coordinated movement patterns, though the enormous size likely limited group cohesion compared to smaller dinosaurs. The ability to communicate through infrasonic calls, similar to modern elephants, may have helped maintain contact across vast distances. The extreme height provided natural protection from most predators, though juveniles would have been vulnerable to large theropods like Allosaurus and Ceratosaurus. Adult Brachiosaurus could likely defend themselves through powerful tail swings or by rearing up on hind legs to bring their full weight down on attackers. Like all sauropods, Brachiosaurus reproduced by laying large eggs, likely in communal nesting sites. The discovery of juvenile specimens reveals dramatic growth rates, with young dinosaurs potentially gaining several tons per year during peak growing periods. This rapid development was necessary to quickly reach sizes that provided safety from predation. Growth studies based on bone histology indicate that Brachiosaurus reached sexual maturity around 20 to 30 years of age and could live for 80 to 100 years. The extended lifespan suggests complex social behaviors and potential intergenerational knowledge transfer within herds. Sustaining such enormous size required remarkable physiological adaptations. The cardiovascular system needed to pump blood up to 13 meters vertically, requiring extraordinary blood pressure and likely a multi-chambered heart system. Recent studies suggest that sauropods may have possessed air sacs connected to their lungs, similar to modern birds, improving oxygen efficiency and reducing body weight. Thermoregulation presented significant challenges for such large animals. The massive body size provided thermal inertia, helping maintain stable internal temperatures, while the long neck and tail may have served as heat exchangers to regulate body temperature in varying environmental conditions. Brachiosaurus represents the pinnacle of sauropod high-browsing adaptation, demonstrating how evolutionary pressures can drive organisms to extreme sizes and specialized feeding strategies. Their success is evidenced by similar body plans evolving independently in other sauropod lineages worldwide, including the African Giraffatitan and South American Argentinosaurus. The extreme gigantism of Brachiosaurus provides insights into the limits of terrestrial vertebrate size and the environmental conditions necessary to support such massive organisms. Their existence demonstrates the incredible productivity of Jurassic ecosystems and the evolutionary potential unleashed during this golden age of dinosaur diversity. Brachiosaurus disappeared from the fossil record near the end of the Jurassic period, approximately 145 million years ago. Climate changes and shifts in plant communities likely contributed to their extinction, as the specialized high-browsing lifestyle made them vulnerable to environmental changes affecting tall-growing vegetation. However, the sauropod lineage continued to thrive throughout the Cretaceous period, with some descendants like Argentinosaurus achieving even greater sizes. The evolutionary innovations pioneered by Brachiosaurus, including the specialized feeding apparatus and gigantic body plan, influenced sauropod evolution for millions of years. Brachiosaurus remains one of paleontology's most remarkable discoveries, representing the ultimate expression of herbivorous gigantism in terrestrial ecosystems. Their unique adaptations for high browsing, extraordinary size, and successful domination of late Jurassic landscapes make them enduring symbols of dinosaur magnificence. The continued study of Brachiosaurus provides crucial insights into the limits of animal size, the dynamics of ancient ecosystems, and the remarkable diversity of evolutionary solutions to environmental challenges, ensuring their place as icons of the prehistoric world and testament to life's incredible potential for adaptation and growth. Spinosaurus, meaning spine lizard, represents one of the most extraordinary and controversial dinosaurs ever discovered. First identified in 1912 by German paleontologist Ernst Stromer in Egypt, this massive theropod has undergone dramatic reinterpretations as new fossil evidence emerges. Distinguished by its enormous sail-like structure and semi-aquatic adaptations, Spinosaurus challenges traditional concepts of large predatory dinosaurs and represents a unique evolutionary experiment in dinosaur ecology. Spinosaurus lived during the Middle Cretaceous period, approximately 112 to 94 million years ago, spanning the Albian to Cenomanian stages. Fossil remains have been discovered primarily in North Africa, including Egypt, Morocco, Tunisia, and Algeria, with the most significant specimens found in the Kem beds of Morocco and the Bahariya Formation of Egypt. During the Mid-Cretaceous, North Africa was dramatically different from today's desert landscape. The region featured extensive river systems, vast wetlands, and tropical coastal environments with high humidity and warm temperatures. Large rivers meandered through lush floodplains, creating delta systems that supported diverse aquatic and terrestrial ecosystems. This environment was home to massive fish, crocodilomorphs, and other aquatic reptiles that would become Spinosaurus's primary prey. Spinosaurus was truly gigantic, with recent estimates suggesting lengths of 15 to 18 meters and weights of 7 to 20 tons, potentially making it one of the largest predatory dinosaurs ever known. The most distinctive feature was the enormous neural spines extending from the vertebrae, reaching up to 1.7 meters in height and forming a spectacular sail-like structure along the back. Recent fossil discoveries have revolutionized our understanding of Spinosaurus anatomy. Unlike other large theropods, Spinosaurus possessed relatively short hind legs, paddle-like feet with webbed toes, dense bones for ballast, and a crocodile-like skull with conical teeth perfect for catching fish. The nostrils were positioned high on the skull, allowing breathing while partially submerged. The arms were proportionally longer and more robust than those of other large theropods, with powerful claws adapted for grasping slippery prey. The tail, recently discovered to be tall and paddle-shaped, served as the primary propulsion system for swimming, fundamentally changing our perception of this dinosaur from terrestrial hunter to semi-aquatic predator. Spinosaurus was primarily piscivorous, fish-eating, representing a unique ecological niche among large theropod dinosaurs. The elongated skull, conical teeth, and powerful neck muscles were perfectly adapted for catching large fish in ancient river systems. Fossil evidence includes fish scales found with Spinosaurus remains and bite marks on contemporaneous fish fossils. The diet likely included massive fish such as the 6-meter Onchopristis, a giant sawfish, coelacanth, and lungfish that inhabited North African waterways. However, Spinosaurus was opportunistic and probably supplemented its diet with smaller dinosaurs, pterosaurs, and other available prey when encountered on land. The feeding strategy likely involved wading in shallow waters, using the sensitive snout to detect fish movements, then striking with lightning speed to capture prey. The powerful arms and claws could secure struggling fish, while the crushing bite force processed the catch efficiently. Recent biomechanical studies confirm that Spinosaurus was uniquely adapted for a semi-aquatic lifestyle among large theropods. The dense bones provided negative buoyancy, allowing the dinosaur to remain submerged while hunting. The paddle-like tail enabled efficient swimming, while the webbed feet provided additional propulsion and stability in aquatic environments. Evidence suggests Spinosaurus spent considerable time in water, potentially diving to depths of several meters while pursuing prey. The high nostril position and specialized inner ear structure supported underwater activities, while the massive sail may have served for thermoregulation, helping maintain body temperature during extended aquatic forays. On land, the short legs and unusual proportions suggest Spinosaurus moved differently than other large theropods, possibly adopting a more quadrupedal stance when terrestrial. This unique locomotion reflects the specialized aquatic adaptations that distinguished Spinosaurus from all other known dinosaurs. The massive dorsal sail remains one of paleontology's most debated features. Several hypotheses explain its function: thermoregulation for maintaining optimal body temperature in varying aquatic and terrestrial environments, display structure for species recognition and intimidation, fat or muscle storage for energy reserves, or a combination of these purposes. Recent studies suggest the sail was covered with skin and blood vessels, supporting the thermoregulation hypothesis. The structure may have been brightly colored, serving both physiological and behavioral functions in the complex social dynamics of these massive predators. Like other dinosaurs, Spinosaurus reproduced by laying eggs, though direct evidence of nesting behavior remains limited. Growth studies indicate rapid development during juvenile years, with the distinctive sail developing as individuals matured. The semi-aquatic lifestyle likely influenced nesting site selection, with adults choosing elevated areas safe from flooding but near productive aquatic hunting grounds. The extended developmental period and large brain size relative to other theropods suggest complex behaviors, including potential teaching of aquatic hunting techniques to offspring and sophisticated navigation abilities in river systems. Spinosaurus represents a remarkable evolutionary experiment, demonstrating how theropod dinosaurs could adapt to aquatic environments while maintaining their predatory lifestyle. This specialization shows the incredible plasticity of dinosaur evolution and the diversity of ecological niches occupied during the Mesozoic era. The unique adaptations of Spinosaurus provide insights into how large predators can exploit aquatic resources, paralleling the evolution of semi-aquatic mammals like hippos and pinnipeds. This convergent evolution highlights the advantages of aquatic hunting strategies for large vertebrates. Spinosaurus shared its environment with diverse fauna including the massive crocodilomorph Sarcosuchus, various fish species, pterosaurs, and other dinosaurs. The aquatic specialization likely reduced direct competition with terrestrial predators like Carcharodontosaurus, allowing multiple large predators to coexist through niche partitioning. The study of Spinosaurus has been complicated by the loss of original specimens during World War II bombing of Munich. Recent discoveries, particularly the 2014 specimen from Morocco, have provided crucial new data, though many aspects of Spinosaurus biology remain controversial and subject to ongoing research and debate. Spinosaurus stands as one of paleontology's most fascinating discoveries, challenging traditional views of dinosaur ecology and behavior. Its unique semi-aquatic adaptations, massive size, and specialized feeding strategies demonstrate the remarkable diversity of evolutionary solutions to environmental challenges. As new discoveries continue to reshape our understanding, Spinosaurus remains a testament to the incredible adaptability and innovation that characterize dinosaur evolution, representing a truly unique chapter in the history of life on Earth. Ankylosaurus, meaning fused lizard, represents one of the most heavily armored creatures ever to walk the earth. First discovered in 1906 by American paleontologist Barnum Brown in Montana, this magnificent herbivorous dinosaur has earned the nickname "living tank" due to its extraordinary defensive adaptations. As the largest and most famous member of the Ankylosaur family, Ankylosaurus demonstrates the ultimate evolutionary response to predation pressure during the age of giant carnivorous dinosaurs. Ankylosaurus lived during the very end of the late Cretaceous period, approximately 68 to 66 million years ago, during the Maastrichtian stage. This places them among the last dinosaurs to exist before the mass extinction event, making them contemporaries of Tyrannosaurus Rex and Triceratops. Fossil remains have been discovered across western North America, including Montana, Wyoming, Alberta, and Saskatchewan. During the late Cretaceous, the climate was warm and humid with high sea levels and no polar ice caps. Ankylosaurus inhabited the coastal plains and river deltas of Laramidia, characterized by lush subtropical forests, extensive wetlands, and diverse plant communities. This environment supported complex ecosystems with numerous herbivorous species and formidable predators, creating intense evolutionary pressure that favored heavily armored prey animals. Ankylosaurus was truly massive, measuring 6 to 8 meters in length, 2 meters in width, and 1.7 meters in height, with adults weighing between 4 to 8 tons. The body was extraordinarily broad and low-slung, creating a tank-like profile that maximized defensive capabilities. The most distinctive feature was the comprehensive body armor consisting of hundreds of bony plates called osteoderms embedded in the skin. These osteoderms varied in size and shape, from small pebble-like nodules to large rectangular plates, creating an virtually impenetrable protective shell across the back, sides, and tail. Even the eyelids were armored with specialized bony shutters that could protect the eyes during attacks. The head was triangular and heavily armored, with additional spikes projecting from the rear corners of the skull. The most fearsome weapon was the massive tail club, formed by enlarged osteoderms fused into a solid bony mass weighing up to 60 kilograms. This club was supported by strengthened tail vertebrae and powerful muscles, creating a devastating defensive weapon capable of breaking the bones of attacking predators. As a herbivore, Ankylosaurus possessed specialized feeding adaptations suited to processing tough plant material. The broad, flat skull housed a relatively small brain but accommodated extensive jaw muscles and a complex dental battery. The teeth were small and leaf-shaped, designed for cropping and initial processing of vegetation rather than extensive chewing. The diet consisted of low-growing plants including ferns, cycads, early flowering plants, and coniferous shoots. The low-slung body and flexible neck allowed efficient browsing on vegetation up to 1 meter high. The wide gut cavity housed an extensive digestive system capable of fermenting tough plant fibers, similar to modern herbivorous mammals. Daily food requirements were substantial. Estimates suggest adult Ankylosaurus needed to consume 100 to 200 kilograms of plant matter daily to maintain their massive, armored bodies. The specialized digestive system required long processing times, making Ankylosaurus relatively sedentary compared to other herbivorous dinosaurs. Ankylosaurus possessed one of the most sophisticated defensive systems in the animal kingdom. When threatened, they could hunker down close to the ground, presenting an impenetrable armored surface to attackers while protecting the vulnerable underside. The low center of gravity made it nearly impossible for predators to flip them over. The tail club served as an active defense weapon, capable of swinging in wide arcs with tremendous force. Biomechanical studies suggest the club could generate impact forces sufficient to shatter the leg bones of large theropods like Tyrannosaurus Rex. The positioning of the club at the end of a flexible tail allowed strikes at multiple angles, creating a dangerous zone around the animal. Recent studies indicate that different ankylosaur species may have exhibited territorial behavior, using their tail clubs in intraspecific combat for dominance or mating rights. Healed fractures in fossil specimens support evidence of both defensive encounters with predators and aggressive interactions between individuals. Evidence suggests Ankylosaurus may have lived in small family groups or loose aggregations, particularly during feeding or migration. The heavily armored body limited mobility, making large herd formations impractical. However, trackway fossils indicate coordinated movement patterns among multiple individuals. Communication likely occurred through visual displays involving the arrangement of armor plates, low-frequency vocalizations that could travel long distances, and possibly chemical signals. The complex nasal passages suggest a well-developed sense of smell for detecting both food sources and potential threats. Ankylosaurus reproduced by laying eggs, likely in well-hidden nests protected by the armored parents. Juvenile specimens show that the characteristic armor developed gradually, with young animals being more vulnerable to predation than heavily protected adults. This extended developmental period suggests significant parental care and protection. Growth studies indicate that Ankylosaurus experienced steady growth throughout their lives, continuously adding armor thickness and developing more sophisticated defensive capabilities. The tail club was among the last features to fully develop, reaching maximum effectiveness only in mature adults. The Ankylosaur body plan proved remarkably successful, with various species flourishing across multiple continents throughout the Cretaceous period. Ankylosaurus represents the culmination of this evolutionary line, showcasing the most advanced armor and weaponry developed by any terrestrial herbivore. The success of heavily armored herbivores like Ankylosaurus demonstrates the evolutionary arms race between predators and prey during the late Cretaceous. As theropod dinosaurs grew larger and more formidable, herbivorous species developed increasingly sophisticated defensive strategies. Ankylosaurus coexisted with some of the most powerful predators ever known, including Tyrannosaurus Rex, Albertosaurus, and Dromaeosaurus. Fossil evidence of bite marks and damaged bones reveals intense predator-prey interactions, though the heavily armored Ankylosaurus was likely a dangerous and challenging target even for the largest carnivores. The defensive capabilities were so effective that successful predation probably required coordinated attacks by multiple predators or targeting of juveniles and weakened individuals. The evolutionary success of Ankylosaurus demonstrates that their defensive strategy was highly effective against contemporary threats. Ankylosaurus became extinct 66 million years ago during the mass extinction event that ended the age of dinosaurs. Despite their impressive defensive adaptations, they could not survive the catastrophic environmental changes caused by the Chicxulub asteroid impact. The legacy of Ankylosaurus extends beyond their prehistoric existence as symbols of evolutionary innovation in defensive strategies. Their unique adaptations continue to inspire biomimetic research and provide insights into the remarkable diversity of solutions that evolution can produce. Ankylosaurus stands as one of evolution's most impressive defensive masterpieces, representing the ultimate development of armor and weaponry in terrestrial herbivores. Their combination of passive protection through comprehensive body armor and active defense via the devastating tail club created virtually impregnable protection against even the largest predators. The success of Ankylosaurus demonstrates that defensive strategies can be just as evolutionarily successful as predatory adaptations, contributing to the incredible diversity of dinosaur forms and behaviors. As one of the last great dinosaurs before extinction, Ankylosaurus represents both the peak of defensive evolution and the end of an extraordinary chapter in Earth's biological history. Allosaurus, meaning different lizard, stands as one of the most fearsome and successful predatory dinosaurs of the Mesozoic era. First discovered in 1877 by paleontologist Othniel Charles Marsh during the famous Bone Wars, this magnificent theropod has become synonymous with Jurassic predation. Distinguished by its powerful build, razor-sharp teeth, and distinctive skull horns, Allosaurus dominated the late Jurassic ecosystems as the ultimate apex predator of its time. Allosaurus lived during the late Jurassic period, approximately 155 to 145 million years ago, spanning the Kimmeridgian to Tithonian stages. This places them in the golden age of dinosaur diversity, coexisting with iconic species like Stegosaurus, Brachiosaurus, and Diplodocus. Fossil remains have been discovered primarily in the western United States, particularly in Colorado, Utah, Wyoming, and Montana, within the famous Morrison Formation. The late Jurassic climate was significantly warmer and more humid than today, with high atmospheric carbon dioxide levels and no polar ice caps. The landscape consisted of vast river systems, seasonal floodplains, and extensive coniferous forests interspersed with fern prairies and cycad groves. This lush environment supported diverse ecosystems capable of sustaining both massive herbivorous sauropods and formidable predators like Allosaurus. Allosaurus was an impressive predator, with adult specimens reaching lengths of August 5, 12 meters and heights of 3 to 4 meters, weighing between 2 to 5 tons. The body was built for active predation, featuring long, powerful legs designed for pursuit hunting and sharp turns. The distinctive skull measured up to 90 centimeters in length and housed formidable weaponry perfectly adapted for killing large prey. The most recognizable features were the prominent bony ridges above the eyes, often called horns, which gave Allosaurus a distinctive and intimidating appearance. The skull was relatively lightweight but incredibly strong, with large fenestrae, openings, that reduced weight while maintaining structural integrity. The powerful jaws contained 70 to 80 curved, serrated teeth designed for slicing through flesh and bone. The arms were proportionally longer and more robust than those of later giant theropods like T. rex, featuring three-fingered hands equipped with large, curved claws up to 25 centimeters long. These powerful forelimbs were capable of grappling prey and inflicting serious wounds during attacks. Allosaurus was an active predator specializing in hunting large herbivorous dinosaurs that shared its ecosystem. Primary prey likely included stegosaurs like Stegosaurus and Kentrosaurus, as well as smaller sauropods such as Camarasaurus and Diplodocus juveniles. The robust build and powerful bite force, estimated at 1,500 to 3,400 newtons, were well suited for attacking heavily defended prey. Fossil evidence, including bite marks on Stegosaurus bones and healed wounds on Allosaurus specimens, confirms intense predator-prey interactions. The hunting strategy likely involved using speed and agility to approach prey, then deploying the powerful arms and claws to grasp and subdue victims while the massive jaws delivered killing bites. Recent studies suggest Allosaurus may have exhibited pack hunting behaviors, particularly when targeting large sauropods. Coordinated attacks by multiple individuals could overcome prey many times larger than individual predators, similar to modern wolves or lions hunting large herbivores. Evidence suggests that Allosaurus may have exhibited complex social behaviors, including potential pack hunting and territorial displays. The discovery of multiple individuals at single sites, along with trackway evidence, supports theories of coordinated group activities. However, the extent of social cooperation remains debated among paleontologists. The prominent skull horns likely served multiple purposes beyond intimidation, including species recognition, dominance displays, and intraspecific combat. Healed fractures and bite marks on Allosaurus skulls indicate that these predators engaged in violent encounters with both prey and members of their own species. Brain case studies reveal that Allosaurus possessed well-developed areas associated with vision, balance, and coordination, supporting theories of intelligent hunting behaviors and complex social interactions within groups. Like all theropod dinosaurs, Allosaurus reproduced by laying eggs, likely in ground nests that may have received some degree of parental protection. Growth studies based on bone histology reveal rapid development during juvenile years, with young Allosaurus experiencing dramatic size increases as they matured. Juvenile specimens show different proportions than adults, with relatively longer legs and smaller heads, suggesting that young Allosaurus occupied different ecological niches and may have hunted smaller prey than their parents. This age-based niche partitioning could have reduced intraspecific competition and allowed multiple generations to coexist in the same territories. Allosaurus represents a crucial stage in theropod evolution, showcasing the successful predatory body plan that would influence carnivorous dinosaur development for millions of years. The balance of size, speed, and weaponry demonstrated by Allosaurus established the template for large terrestrial predators throughout the Mesozoic era. The success of Allosaurus is evidenced by their widespread distribution, abundance in the fossil record, and evolutionary longevity spanning approximately 10 million years. This remarkable success demonstrates the effectiveness of their hunting strategies and ecological adaptations. Allosaurus played a crucial role in late Jurassic ecosystem dynamics as the primary predator of large herbivorous dinosaurs. The evolutionary arms race between Allosaurus and heavily defended prey like Stegosaurus drove remarkable adaptations on both sides, with predators developing more sophisticated hunting strategies while prey evolved increasingly effective defensive mechanisms. The coexistence of multiple large predators, including Allosaurus, Ceratosaurus, and Torvosaurus, suggests complex ecological relationships and niche partitioning that allowed several apex predators to thrive simultaneously in the same environments. The Morrison Formation has yielded numerous Allosaurus specimens, making it one of the best-known theropod dinosaurs. Famous discoveries include Big Al, a nearly complete skeleton that provided crucial insights into Allosaurus anatomy and pathology, and various mass death assemblages that suggest social behaviors. The abundance of Allosaurus fossils has enabled detailed studies of growth patterns, individual variation, and population dynamics, contributing significantly to our understanding of theropod biology and behavior. Allosaurus disappeared from the fossil record near the end of the Jurassic period, approximately 145 million years ago, likely due to climate changes and shifts in prey availability as ecosystems transitioned into the Cretaceous period. However, their evolutionary legacy continued through descendant lineages that would produce even larger predators during the Cretaceous. The hunting strategies and body plan innovations pioneered by Allosaurus influenced theropod evolution for the remainder of the Mesozoic era, with later giants like Tyrannosaurus Rex building upon the successful predatory template established by these Jurassic hunters. Allosaurus stands as one of paleontology's most significant predatory dinosaurs, representing the pinnacle of Jurassic carnivorous evolution. Their combination of size, speed, intelligence, and weaponry made them formidable apex predators capable of dominating diverse ecosystems for millions of years. The successful hunting strategies, potential social behaviors, and evolutionary innovations of Allosaurus provide crucial insights into the complex predator-prey dynamics that shaped Mesozoic ecosystems. As one of the most thoroughly studied theropods, Allosaurus continues to enhance our understanding of dinosaur biology, behavior, and the remarkable diversity of predatory adaptations that evolved during the age of dinosaurs. Parasaurolophus, meaning near-crested lizard, stands as one of the most extraordinary and acoustically sophisticated dinosaurs ever discovered. First identified in 1922 by Canadian paleontologist William Parkes in Alberta, this remarkable hadrosaur has revolutionized our understanding of dinosaur communication and social behavior. Distinguished by its distinctive hollow crest that functioned as a natural musical instrument, Parasaurolophus represents the pinnacle of evolutionary adaptation in both herbivorous feeding strategies and complex acoustic communication systems during the late Cretaceous period. Parasaurolophus lived during the late Cretaceous period, approximately 76 to 73 million years ago, specifically during the Campanian stage. This places them in one of the most diverse periods of dinosaur evolution, coexisting with iconic species including Triceratops, various tyrannosaurs, Edmontosaurus, and numerous other herbivorous and carnivorous dinosaurs that populated North American ecosystems. Multiple species of Parasaurolophus have been identified across different time periods and geographic locations. Fossil remains have been discovered throughout western North America, with significant specimens found in Alberta and Saskatchewan, Canada, as well as Montana, New Mexico, Utah, and Wyoming in the United States. The most complete specimens come from the Dinosaur Park Formation in Alberta and the Kirtland Formation in New Mexico, providing exceptional insights into the anatomy and lifestyle of these remarkable creatures. During the late Cretaceous, North America was divided by the Western Interior Seaway, creating the western landmass of Laramidia where Parasaurolophus thrived. The climate was considerably warmer and more humid than today, with high atmospheric carbon dioxide levels, elevated sea levels, and no polar ice caps. This greenhouse world supported lush subtropical forests, extensive river systems, coastal plains, and diverse wetland environments that provided ideal habitats for large herbivorous dinosaurs. Parasaurolophus was a substantial dinosaur, with adult specimens measuring 9 to 10 meters in length and reaching heights of 3 to 4 meters at the hips, weighing approximately 2.5 to 4 tons. The body structure was typical of advanced hadrosaurs, featuring a robust build perfectly adapted for both bipedal locomotion when running from predators and quadrupedal stance during feeding activities. The most distinctive and scientifically significant feature was the elongated, hollow crest extending backward from the skull. This extraordinary structure varied considerably among different species and age groups, ranging from 1 to 2 meters in length. Parasaurolophus walkeri possessed the longest and most curved crest, while P. tubusan featured a shorter, more upright structure, and P. certicristus displayed an intermediate form with a distinctive forward curve. The internal anatomy of the crest represents one of the most sophisticated acoustic systems ever evolved in the animal kingdom. Complex air passages wound through the hollow interior, connecting the nasal cavity to the throat and creating an intricate resonating chamber comparable to modern brass instruments. Recent CT scanning and computer modeling have revealed the precise internal geometry, demonstrating how different species could produce distinct tonal ranges and harmonic structures. The skull was elongated and duck-like, housing one of the most advanced dental systems ever developed by herbivorous animals. Each jaw quadrant contained up to 300 small, diamond-shaped teeth arranged in complex batteries that created efficient grinding surfaces. These teeth were continuously replaced throughout the animal's lifetime, ensuring optimal processing efficiency for tough plant material. The broad, flat duck bill was covered with a keratinous sheath similar to modern waterfowl, perfectly adapted for selective cropping of vegetation. Parasaurolophus was a highly specialized herbivore with remarkable feeding adaptations that allowed them to efficiently process a wide variety of plant materials. The sophisticated dental batteries represented the pinnacle of herbivorous dental evolution, creating grinding surfaces more complex than those found in any modern mammal. This system allowed Parasaurolophus to extract maximum nutrition from fibrous, cellulose-rich plant tissues. The diet consisted of diverse vegetation including conifers such as pine, fir, and cypress, various ferns and horsetails, cycads, ginkgos, and early flowering plants that were becoming increasingly common during the late Cretaceous. Analysis of fossilized stomach contents and coprolites has revealed that Parasaurolophus consumed substantial quantities of coniferous needles and woody material, indicating an ability to process resinous and chemically defended plant tissues that might deter other herbivores. The feeding strategy involved using the flexible duck-like bill to selectively crop preferred plant parts, followed by extensive processing through the complex dental batteries. The powerful jaw muscles, evidenced by large muscle attachment sites on the skull, provided the force necessary to grind tough stems, bark, and woody tissues. The elongated neck allowed feeding from ground level up to approximately 4 meters high, enabling access to a broad vertical range of plant resources and reducing competition with other herbivorous species. Recent isotopic analysis of Parasaurolophus bones suggests seasonal migration patterns, with these dinosaurs potentially moving between different elevations or latitudes to follow optimal food resources throughout the year. This migratory behavior would have required sophisticated navigation abilities and coordinated group movements across vast distances. The hollow crest of Parasaurolophus represents one of the most remarkable examples of acoustic adaptation in the fossil record. The internal air passages functioned as sophisticated resonating tubes, allowing these dinosaurs to produce complex, low-frequency sounds that could travel long distances through dense forest environments. Computer modeling and physical reconstructions using 3D printed crest replicas have demonstrated that different species could generate distinct tonal ranges, with fundamental frequencies ranging from 48 to 240 Hz. Parasaurolophus walkeri produced the deepest, most resonant tones due to its longest crest, while P. Certicristus generated higher-pitched sounds with more complex harmonic structures. These acoustic differences likely facilitated species recognition, reduced acoustic interference in environments where multiple hadrosaur species coexisted, and enabled sophisticated intraspecific communication including mating calls, territorial displays, and danger warnings. The sounds produced could potentially travel several kilometers through forested landscapes, enabling communication between herd members separated by considerable distances. The complex internal geometry suggests capabilities for producing multiple harmonics, frequency modulation, and potentially sophisticated acoustic signals comparable to the songs of modern birds or the complex vocalizations of marine mammals. Evidence strongly indicates that Parasaurolophus lived in large, organized herds with complex social structures. Fossil discoveries of multiple individuals in close proximity, extensive trackway systems showing coordinated group movements, and bone bed assemblages suggest highly developed social behaviors. Different age groups within herds likely produce distinct acoustic ranges, allowing for age-specific communication, social organization, and potentially hierarchical structures based on acoustic dominance. Parasaurolophus reproduced through egg-laying, with evidence suggesting communal nesting behaviors similar to other hadrosaurs. Recent discoveries of hadrosaur nesting sites have revealed sophisticated colonial breeding strategies, with adults potentially providing extended parental care including nest protection, feeding assistance, and predator defense for vulnerable juveniles. Growth studies based on bone histology reveal fascinating developmental patterns in crest formation and acoustic capabilities. Juvenile specimens possessed small, solid crests that gradually became hollow and elongated as they matured. This ontogenetic development suggests that full acoustic communication capabilities were primarily adult functions, possibly related to sexual selection, mating behaviors, and social dominance hierarchies. The extended developmental period, estimated at 15 to 20 years to reach full adult size, combined with evidence of parental care, indicates remarkably complex social structures within Parasaurolophus herds. Experienced adults potentially taught foraging techniques, predator avoidance strategies, and acoustic communication skills to younger individuals, creating cultural transmission of knowledge across generations. Sexual dimorphism in crest size and shape has been proposed, with some researchers suggesting that males possessed larger, more elaborate crests for acoustic dominance displays and mate attraction. However, this interpretation remains controversial, as the observed variation might represent species differences, individual variation, or age-related changes rather than sexual dimorphism. Parasaurolophus inhabited ecosystems populated by formidable predators including various tyrannosaurs such as Albertosaurus and Gorgosaurus, swift dromaeosaurs, and cunning troodontids. The combination of herding behavior, sophisticated acoustic warning systems, and impressive running capabilities provided effective anti-predator adaptations. When threatened, Parasaurolophus herds could potentially create overwhelming acoustic displays to confuse predators while facilitating coordinated escape responses. The low-frequency alarm calls could simultaneously alert distant herd members and potentially disorient attacking predators through acoustic overload. The bipedal running capability, reaching estimated speeds of up to 40 to 45 km per hour, made them challenging prey even for the swiftest predators. Group coordination provided additional protection through collective vigilance, with multiple individuals monitoring for threats while others fed. The acoustic communication system enabled rapid transmission of danger signals across entire herds, allowing coordinated responses to predator attacks including defensive formations and strategic escape routes. Parasaurolophus represents the evolutionary pinnacle of Lambeosaurine hadrosaurs, showcasing remarkable adaptations that combined advanced herbivorous processing capabilities with sophisticated acoustic communication systems. The success of this lineage demonstrates the evolutionary advantages of integrating efficient feeding strategies with complex social coordination mechanisms. The diversity of crest shapes and acoustic capabilities among closely related Parasaurolophus species illustrates rapid evolutionary radiation driven by acoustic specialization. This provides valuable insights into how communication systems can drive speciation, ecological diversification, and adaptive radiation in vertebrate lineages. Phylogenetic analyses place Parasaurolophus within the Lambeosaurine subfamily of hadrosaurs, closely related to other crested forms such as Lambeosaurus and Corythosaurus. The evolution of hollow crests represents a major innovation that distinguished Lambeosaurines from their solid crested relatives, enabling acoustic communication capabilities that likely contributed to their ecological success. Parasaurolophus disappeared from the fossil record approximately 73 million years ago, well before the final Cretaceous-Paleogene mass extinction event. Climate changes, shifting plant communities, and increasing competition from other herbivorous dinosaur lineages likely contributed to their decline. Their specialized feeding requirements and habitat preferences may have made them particularly vulnerable to environmental changes affecting late Cretaceous ecosystems. However, the evolutionary innovations pioneered by Parasaurolophus, particularly in acoustic communication and social organization, influenced hadrosaur evolution and provide remarkable insights into dinosaur behavior. Their sophisticated communication systems challenge traditional perceptions of dinosaurs as primitive creatures, demonstrating that these ancient animals possessed complex social behaviors comparable to modern highly intelligent vertebrates. Parasaurolophus stands as one of paleontology's most extraordinary discoveries, representing a unique convergence of advanced herbivorous adaptations and sophisticated acoustic communication systems that revolutionized our understanding of dinosaur intelligence and social behavior. Their remarkable hollow crests, functioning as natural musical instruments capable of producing complex harmonic structures, demonstrate that late Cretaceous ecosystems supported intricate social networks and communication systems rivaling those of modern highly social mammals and birds. The success of Parasaurolophus in diverse late Cretaceous environments, combined with their advanced feeding strategies, acoustic capabilities, and complex social organizations, illustrates the remarkable evolutionary potential achieved during the golden age of dinosaur diversity. As one of the most acoustically gifted and socially sophisticated dinosaurs ever discovered, Parasaurolophus continues to provide invaluable insights into prehistoric behavior, the evolution of communication systems, and the extraordinary diversity of biological solutions that emerged during the Mesozoic era. Thank you so much for watching. Don't forget to like the video, subscribe to the channel, and drop a comment below to let us know what content you'd love to see next.